In this recording and lecture, I'm going to continue our discussion of how to compute beam deflections, and specifically the segment is going to be about a numerical method that is affiliated with finite element analysis. So in a way, I'm taking this opportunity to not only for you to be introduced to a numerical method, but also to teach a little bit about the elements of finite element method for beams, because beams are simple one-dimensional materials or bodies, and we will see that in your projects you may be using COMSOL or Abacus to do the full finite element analysis for determining stresses and strains and displacement. So it will be useful for us to continue the deflection calculations since we're familiar with the equations now, but put it in a framework where finite element method is used. And for me to do that, I'm going to use the material developed by Professor Sean Salisbury from Western University in Canada. So to give him proper credit, here is his website. He's assistant professor at Western University, and he teaches also design, and he developed a MATLAB program that I found to be very useful on beam analysis, and that's why I just decided to use it from his website. So we're going to go through the document that I will have on our website with credit to him, and it will teach us how to do finite element calculations on first a simple example of spring elements, a bunch of springs connected together, and we'll assemble those. Once we understand the method on spring elements, then we will take the beam and divide it into segments or pieces or elements, if you will, and then develop equations for each piece and then assemble this together. And finally, we will go over some of the intricacies of the MATLAB program. It also will help us strengthen our programming techniques, and the program is available for us to, courtesy of Professor Salisbury, to use for calculations involving deflections of shafts that have complicated properties. So let's see what we have here. So as you can see, we're going to start first with a very quick review of how linear equations are solved, and then we will focus on the simple example of one-dimension spring elements, and then we will get finally into the beam elements and then the MATLAB code. So that's kind of the procedure. So how do you solve systems of equations? A system of equation, we put it linear equations, is that we put it in a matrix vector form, as you can see here. So it is K times U equals F. So K is a matrix, so a matrix like a square matrix, and U is a vector, so it will be a vector. So this will be a matrix full of numbers here, and this is just a column vector, and F is also a column vector, so I will have numbers here. So as we know from our previous experience, there are so many methods to solving linear systems. The easiest way now is to use MATLAB, and MATLAB has two different ways that if you take K to the other side, you have to invert it. So you have U is equal to inverse of K times F, and that will be the statement that is used to solve the system of linear equations. However, when the vector U and F are very large, then this method is very slow. So MATLAB uses a different technique by Gaussian elimination, and the solution is obtained by a simple command. U is equal to K /F. So it's like division, but kind of a special division because you have K is a matrix and F is a vector or a row or a column matrix, if you will. So let's apply that because we will use the same equation once we assemble the matrices, and let's apply that to one-dimensional spring elements. So one-dimensional spring element is, as you can see here, is one. We're going to take one element here. We're going to call a spring, which has a stiffness K sub e, and then it has two nodes, one from the left, one from the right, and each node has two things: the displacement in the x direction, u1, and the force in the x direction, f1. And the end node is displacement is u2, and the force is f2. So if I write an equation describing the relationship between, these are internal forces, so F is internal. In other words, it's like a free body. When you just cut the free body, that's the internal forces inside, because the spring is cut out of many other springs, as we will see. So if we write, we know that the equation for a spring is K times delta X, right? The F is equal to K times delta X. Delta X is the change in length, which is U1 minus U2, and K is the K of the spring. And then if I want to write F2, this is F1. If I want to write F2 applied to node 2, then it would be K times delta X referred to node 2, which is minus U2 plus U1. So in other words, we have two equations for that element, and the two equations are for the force equals to K delta X, and delta X is for each side of the node as we measure from there. So if we want to write these two linear equations in a matrix form, we could write them such that the F will be a vector on one side. So we have this will become a vector. Let's say F vector will be equal to, it has two components, F1 and F2. And then the U is another vector. It has two components, U1 and U2. And then we can form a matrix K that will, when it's multiplied by U, it should give us these two equations. So since we have Ke times U1, so this has to be positive, and minus U2, then it would be minus Ke. And then for the second equation, we will have minus Ke and Ke. And that's basically a representation of the stiffness matrix. So if you write it down, you see that the stiffness matrix here is represented, and we have the linear set system of equations is cast in a more compact form that has the K matrix times the U vector equals to the force vector. So force is on the right side and displacement is on the left side multiplied by the stiffness matrix. That's the simplest approach, right? So now let's see that we want to go to different elements in the spring elements that connected together. So if we have different spring elements connected together, consider only two of them for illustration. We have element 1 and then element 2. These are connected together. Element 1 has these nodes. U1 and U2 are the displacements at these nodes. F1 is the external force at the node. F2 is the external force at the node. And then at the end of element 2, we have U3 is the displacement, and the external force is F3. So we're going to use a notation that F, lowercase f, at node 1, which is the left, of element 1. So F1, this means node 1, and this is element 1. And then when we have F2, 1, this is second node, which is at the end of the element, and this is again element 1. Element 1. So with that, we can rewrite the equations as if this element here is separate by itself. So if separate by itself, we would write it exactly the same as we did for a single spring, that is stiffness matrix times the displacement vector is equal to the force vector. Now this force vector is internal forces. We'll come to that point in a little bit. And then we can also do the same thing for the second element, which is that spring element here, which is element 2. So you can see that the second index is 2 right here, is indicating that we are element 2, and the nodes is 2 and 3, which indicates the number of nodes. So we have node 1, node 2, node 3 here, and these are the numbers. So now that's fine. We have separate equations for each element. Now we would like to connect them together, and in order for us to connect them together, we will use the equilibrium to connect external forces to internal forces. So if you look at the first equation here, this tells us that the external force at node 1 must be equal to the internal force because it's the only one that exists there. And the external force at node 3 must be equal to the internal force at node 3. However, for node 2, which connects the two elements together, the external force must be equal to the sum of the two internal forces. So this notation, we can replace the two sets of equations, like these two sets of equations, with only one set. So how do we do that? We want to make a bigger matrix. So what we want to do is we would like to create a vector that has a displacement vector that has u1 and u2 and u3, because it's only the three displacements. So u1, u2, u2 is repeated, and u3. And then we want to find a force vector. Now we're going to have F1 and F2 and F3. And note that F1 and F3 are the same as internal nodes, but F2 is the sum of the internal forces. So with that, we can rewrite the two sets of equations into one. And if you notice here, you will see that I have a matrix here. I'm going to try to highlight it. So I'll expand it a little bit to highlight it in here. So you have a matrix, and this matrix is represented by this one. And then when we add the second matrix, then we actually shift the position of the first element of the matrix to the corner where the overlay. So you have a matrix here. This is the first matrix, and then a second one that comes in here. So there's a little shift as we add. What the rest of the matrices will be 0, and therefore the structure is that we can create as many as needed with some overlap with the sum in between, and you can see the overlap is right here on the connection between U2. Otherwise, the two matrices are almost identical, except for the first one has K1, right? And then the second one has K2, as you can see here. So that's kind of the structure that would be useful when we come to the MATLAB program, as we will see in a little bit. Basically, that's the way we form it. This is the assembly process. The assembly process is that you augment the element matrix with zeros, as many zeros as needed to fill in for the number of elements that we have in our system. So how many we have here? We have actually 3 nodes. So if you see here, node 1, node 2, and also node 3. And each node has 1 degree of freedom. So 1 degree of freedom. Therefore, we need 3 equations, and 3 unknowns. And therefore, the matrix, stiffness matrix K, has to be 3 by 3. And that's why we fill the zeros, 3 zeros here, and also we fill 3 zeros here, and then overlap the middle elements there. So the end of matrix 1 should overlap with the beginning of matrix 2 with that shift. So in programming, in MATLAB programming, we'll use this trick to assemble the matrix. If we have 3 nodes, now we got the idea. If we have three elements, which is 4 nodes, it will be 4 by 4. And again, you get the corner, another corner here, and you just do the overlap. So let's now study a spring example. And the spring example will illustrate what's needed with the boundary condition. So what I found is that's interesting about this procedure is that if I do this, I can set up now the system, right? Because I have a number of nodes connected with the springs, and each one spring has a very simple 2 by 2 matrix, stiffness matrix, multiplied by the displacements, give me the internal forces, and then when I assemble, then I can convert internal forces to external, and also I can formulate one total vector that has the number of unknown degrees of freedom. Generally, the unknown degrees of freedom will be the displacements. So now I have a couple of comments on the if I'm looking at solving now a problem like this, what I would like to know is the displacements everywhere, and I also would like to know the forces everywhere. However, I cannot solve the problem unless I know imposed forces or imposed displacements from the outside. In other words, I can either dictate what the displacement is at a node given some constraint, or dictate what the force is at a node given some constraint. Such dictation of result is called boundary condition. So a boundary condition could be totally at the ends or somewhere in the middle or anywhere. However, you can only put either a displacement boundary condition, which is called a Dirichlet boundary condition, on the value of the function itself that we solve for, that is the displacement, or you can put in a force boundary condition, and that is the Neumann in general. It's called a Neumann boundary condition, which is a boundary condition on the derivative of the function. In elasticity, the force is like the stress, and the stress has a kind of a derivative of the displacement field. So we can only use one of them at a node. And the question is that how do we solve the set of equations given that? Well, if we have the right-hand side with the specified forces only, for example, external force at node 2 is 50 and node 3 is 100, then there's no problem. I can put 50 on node 1 and then 100 on node 2. But F1 would be the only unknown, like it would be unknown in this case. And also I need to determine 3 unknowns, which is U1, U2, U3. That's not possible because my system is 3 equations and 3 unknowns. Therefore, I need another boundary condition. And the boundary condition here is given to me that at the first node, the displacement is determined to be 3 millimeters. So I have to put now 3 millimeter, like if I just write that down. So I have this as 3 millimeters instead of U1 right here. Then I will have the first line would be 10 U1, 10 times 3 minus 10 times U2 plus 0 times U3 would be equal to F1. But I know U1 already, so why do I need to incorporate this equation? Therefore, I can eliminate the first equation. And my system of equations will be for the second row multiplied by the U vector should give me that number, 50. So 50 is equal to all of this times all of that in the summation mode. That would be, easier. And then you have another equation will be the second row multiplied by this same column will give me 100. Okay, so we could do that by hand, but the thing is that if we're going to use MATLAB, we better kind of stick to a matrix method, because at the end of the day with MATLAB, we need to solve for U. Remember, KU equals F, and in MATLAB we say that U is equal to F, and then you have this back /K. And that's kind of the inversion of the stiffness matrix. That's much easier to write, and therefore we're going to use a little bit of trick to augment the matrix and make it look solvable for MATLAB. And that is by saying that basically we can move this 3 to the other side. So if you, instead of having a 3 by 3, we know the answer. So if we move 3 to the other side, then we can write the two equations for U2 and U3 with the known displacement times the entire stiffness row and put it on the other side. So it would be subtraction. So on the other side would be 50, the original number, minus the result of 3 times minus 10. So it will be minus 10 times 3. And that will modify, so the force components here will be modified by the boundary condition, known boundary condition for displacement. And the same thing, the influence of the 3 on the force at 100 will be 100 minus now this row times 3, the first one times 3, element times 3 will be 0, and therefore you get now the top here you get 80. This gives us 80, modifies the 50 to 80, and this modifies 100 to stay 100 as it is. Therefore, we can rewrite now the set of equations, including the boundary conditions, in the following form. The first row will be 1 in the stiffness matrix that corresponds to the known displacement, and we can put its value on the right hand side. The second and third will be, we have to include zeros in here in the stiffness matrix, so this will be another 0 missing here. And then we modify the load force, the force F2 and F3 with the moving the displacement times the corresponding stiffness to the other side, giving 80 and 100. So that's kind of the procedure. Equation 18 now replaces equation 15, which is supposed to be the describing equation knowing that U1 is equal to 3. So to summarize here, if I know any component of the force vector, I just put it on the right hand side. But this will give us no solution, useful solution, because it will translate the entire set of springs in a rigid body motion. So we will have to fix the set of springs at some point. We have to give it either zero displacement at some node, or we will have to give it a given displacement at some node. Once we decide that, then the displacement boundary condition makes it a little bit complicated, because we have to move or find the equivalent forces to that displacement. And the process is that we put the displacement, a known displacement, on the row that is assigned to it, and then evaluate it, move it to the other side, which is a force equation, by multiplying it by the corresponding elements in the stiffness matrix, as we did here. So we will continue with this discussion to see how the entire system now looks like. And you see now that my system has this structure 1, 0, 0. So it should be, should be a 0 here. Minus 10, 30, minus 20. 0, minus 20, 20. That's the stiffness matrix augmented for the entire system. 3 is the displacement that is known. These are unknown displacements we solved for. And the external forces are minus 150 we found by the solution. These two were imposed on the nodes. So in summary, we calculate the stiffness matrix for each element. We assemble the stiffness matrix in the total stiffness, the element matrix in the total stiffness matrix. We put the external loads in the load vector. We incorporate the boundary conditions, which are known deflections, in stiffness matrix and load vector, because it has to be both, as we have done before. And then you solve a linear system of equations. So this is kind of the procedure for the case of the simple spring elements. Now let's look at the beam element, which is what we wanted to study in the first place. So our shaft design will be composed of different sections. Each section has constant properties. In other words, it has a moment of second moment of area, and it has an elastic constant. If it is a different material, we can choose different elastic constant. And we want to assign nodes at the beginning and at the end of that beam. And then there's some kind of distribution in between the two nodes. So the beam element method that is presented here is such that we can only assign forces and moments at the end nodes. In other words, in between, we don't assign any values of these forces or moments. So if we have a distribution of forces on a beam element, then we have to do something about it. And the way to do it is that if we have a distribution of forces, we can assign these forces to the nodes. Like we can just add up, integrate over the element, and then take the integration and then split it accordingly to the left node and to the right node. So why are we doing that? Because it makes things simpler to just solve for a beam element that has assigned forces and moments alone, without anything in between. In other words, the moment is constant from going left to right, and then the assigned moment, and then you have another moment coming from an assigned force. And therefore, the solution is analytical. We can write it very simple, and then we can create a matrix, a stiffness matrix for the element from the solution that we have, and then we can assemble it. So let's see how this works in practice here. So what you can see here is that I have a general beam element, and the general beam element has a reaction R1 on the left node and a moment M1 on the left node. And then it has also a reaction R2 on the right node and a moment M2 on the right node. Correspondingly, we have from the slope, we can get a rotation theta 2 and a rotation theta 1. So what we do is we can proceed from left to right or from right to left, exactly like what we did for the spring element. So to create equations for the beam. So let's do it from the left to right first, and then we can extrapolate the idea the other way around. So if I'm going from the left to right, I can take a section at a point X along the beam, and then in this section, then this beam element has to be in equilibrium. So if I have M1 going this way, then I have to have M1 on this side. And then if I have R1 going this way, I have to have R1 also going this side. This is how equilibrium is achieved. So if I'm interested at what's happening at M1, starting from the left side at this point here, then I wanted to write an equation for the slope and for the moment. So the slope at x, at this point x, is equal to initial value theta 1 on the left plus 1 over EI times, well, let me just start the process here from the moment. So the moment at any position x is equal to the moment here minus M1 because the M1 was on applied left side is positive, then on the right side it would be negative. Remember that I have x, y, z, so I have x this way and y is this way and z is out of the board. So the positive sense for the moment is when it is going counterclockwise, and therefore on the right side here M1 is negative, so you have minus M1. So we have minus M1, and then we have the influence of the reaction R1, so it'll be R1 times X. So this is the moment equation that we can build from both the applied moment and from the reaction. And note that this is equal to E times I times Y double prime. So you integrate it once like we did in the course. You get equation 22. You integrate it twice, you get equation 23. And if you look at them, these two equations are actually applicable all the way from x equals 0 to x equals L. L is the length of the beam element. So I have L is the length along the x direction here. So if I substitute x equals L, I will have on this side, this becomes theta 2, and this becomes y2. And everywhere else I can substitute x is equal to L. And therefore I can solve for R1 and M1 in terms of theta 1, theta 2, y1, y2. So this will be equation 23 and 24. I can rewrite them, R1 and M1 on one side, and then some function of these four unknowns or 4 degrees of freedom on the right side. Well, how do we do it? Remember how we did it for the spring element? That was simple because we wrote the spring element had, if you look at this equation here, we see that we have two equations actually that look identical. This equation is obtained from the left node. This equation is obtained from the right node. They pretty much say the same thing because it's like equilibrium, but they help in the assembly process because you obtain them from the left and from the right. And same thing now we can do. It's a little bit had more degrees of freedom. In the previous example, we had only 1 degree of freedom per node, but here every node has 2 degrees of freedom, which is the theta and the y. So these are 2 degrees of freedom for the left and 2 degrees of freedom for the right node, as opposed to only U1 and U2 in the previous example of the spring element. So spring element is gone. Now we have the beam element. So if we look at that, we can also develop 2 other equations. If we go from the right, and these equations will be R2 and M2 as functions of these theta 1, theta 2, y1, y2. Well, this is done for us here, and the final result is equation 24. And equation 24 states that if I look at the right-hand side, is the force vector is now generalized to have proper forces R1 and R2, and also moments applied on the nodes M1 and M2. And on the left side, instead of only given displacements, we have displacements y1 and y2, and we also have the angles of rotation theta 1 and theta 2. And the rest here, all of this, is just a stiffness matrix that will be a bunch of constants. Once we know L and E and I, then we can formulate this stiffness element. So, stiffness matrix. So if we just now proceed exactly like before, we will take an example and maybe stop after this example, because the next segment we will go into the details of the code itself. So let's have a beam example. I have a shaft, and the shaft has shaft 1 has a moment of area, second moment area of 20, and shaft 2 has a second moment of area of 60. And we have one end of the shaft, y is equal to 0 on the left side. Also on the right hand side, y will be equal to 0 because it's simply supported. Now, since this is a wall support, we also expect that theta is equal to 0 on the left side. So these are left boundary conditions. This is right boundary condition. And the loading vector is expanded. And the loading vector here, I have the force, which is 6 newtons, and also the moment applied here, which is 50 Newton meter on that node. So if I simplify, instead of making the beam look like this, we will have basically, for computational purposes, we have 3 beam elements, one connecting node 1 to node 2, and then node 2 to node 3, and node 3 to node 4. And we divide it up this way because we wanted to get more detailed information between the applied load and the shoulder of the shaft in this region here. So we were basically forced to make another element in between these 2 positions for obtaining more information. And therefore, I have all of the properties. The E is given, and the L is given, and the I is given for each element. And therefore, we can go back and with these numbers and go back and fill in the element stiffness matrix that we talked about, because every element can be computed easily. And the result is given here. So we have, this is for element 1, this is for 2, this is for 3. And then when we assemble, notice that when we assemble, we just overlay, because we have this guy has to be sent together with this guy. And the same thing here, 2400 will have to be with the beginning with the 20. So you can see that at the corner that we have here, we have 4 by 4. So if we go matrix 4 by 4, this is your 4, and this is another 4, and then you get that corner here, the overlay, and then you have another 4 by 4. So you get, this is the 4. Let's just kind of clear it here, and then we see the 3 4 by 4s. So the 4 by 4, the first 4 by 4 will be this matrix here, and then the second 4 by 4 will be this matrix here. This is here 600, and going this way, and then the third 4 by 4 will be this matrix here. Sorry, they do it this way, and then we have actually the overlay. You can see now the overlay between the matrices. So you have the 4 by 4 and then the 4 by 4. Actually, this one would be, it has to be shifted to accommodate that. So we will have to shift this matrix here, like this line. These have to be shifted for the overlay, and the shifting here will be in between. So we just have to shift this matrix here. Okay, so we have 3 basically shifted matrices that are overlaid, and when we apply the boundary conditions for the system, we obtain first on the right hand side, we have to have the nodal forces and moments, which are given to here. We have -6 at one node and -50 moment at the end node, and we are imposing now 3 boundary conditions: that y1 equals 0, at theta1 equals 0, and y4 equals 0. So when we have y1 equals 0, as we learned, then we take the entire row and replace it with another row that starts with 1, everything else is 0, and modify the load vector everywhere with the stiffness. But luckily, because it's y equals 0, then the numbers, the force vector does not change. And then the same thing with the theta1 equals 0. You can see here I have the entire row, I have a 1 here, and then the entire row is zeros, and the entire column is zeros. And again, because it's 0, then there's no modifications. So in other words, if you have only 0 boundary conditions, then it will be easy because you don't modify the force vector. It's not modified. But if you have given displacements or given rotations, then you have to do modify the right hand side with the application of the given displacement or rotation times the corresponding row of the stiffness matrix, and that gives us an 8 by 8 system, and the 8 by 8 system, a solution of that gives us the displacements and the rotations at the 4 nodes, as you can see in here. Now, if we final result is that if we wanted to construct a MATLAB program, then the MATLAB program should go through this procedure that we've done before, and should also give us the plots for the shear force diagram. Here is the shear force diagram, the bending moment diagram as given to us here, and the slope of that matrix of the beam as well. And also it should give us the final result is the deflection, as you can see here. So we've finished basically the display for the results of what we've wanted to accomplish. And these are the results. Is both the we have 4 different results. We display the shear distribution, the moment distribution, the slope, and the deflection numerically. And that is basically what we wanted to end up doing. So I'm going to stop here, and in the next segment, I'll just show you the code that Professor Salisbury wrote and give you a few comments so that you can understand how it works when you apply it. So we'll see you next time.